Okay, so this is 9.3 tests about a population mean, concept 1. So CFU 9.3, concept 1 on one sample t-test for a population mean. So check for understanding. Students will be able to check conditions for carrying out a test about a population mean. So those three conditions you have to remember how to actually check them. Next, students will be able to conduct a one sample t-test about a population mean. So let's jump in. So humerus bones from the same species of animal tend to have approximately the same length to width ratios. When fossils of humerus bones are discovered, archaeologists can often determine the species of animal by examining these ratios. It is known that the species Moschus primatium exhibits mean ratio of mean equals to 8.9. Suppose 41 fossils of humerus bones are unearthed at a site on Minnesota's Iron Range where this species was known to have lived. Researchers are willing to view this as a random sample of all such humerus bones. The length to width ratios were calculated and are listed below. Test whether the population mean for the species that left these bones differ from 8.9 at an alpha of 0.05. So if you look at this 41 fossils sample data, I immediately put into my list 1. So go to Stat, Edit. So see, I put everything in my list 1. All right, so let's continue. So we'll do a 4-step process, right? So the first thing,
Motion detected.
right, to state, right, the first step of the 4-step process, state. Now we will conduct, or we wish to conduct, a one sample t-test. Now t-test, this is going to be a different YT and not Z. It's because we're given, a sample, right? 41 sample, and the nothing is known of the population, right? Only the parameter, only the that what was it? It's known that the species Moschus primatium exhibits mean ratio of mu equals to 8.9. But the standard deviation is not given. When the standard deviation of the population is not given, we use t-distribution. Okay, that's why we will conduct a one sample t-test for the true mean ratio. And so we need to put H naught, right? The null hypothesis is mean, mu equals to 8.9 versus the alternate hypothesis, HA, is the mean is not equals to 8.9 at a significance level of 0.05. Next thing is the plan, right? After state, we plan. The plan is where you give all your conditions, and there are same number of conditions. There are 3. First one is it random, right? SRS, simple random sample, is that available? There's a sample random sample of 41 bones. And then the next condition is the large count condition. All right, and since the sample size is 41, which is greater than 30. So ladies and gentlemen, when you talk about mean, right, this is not proportion. When you talk about a quantitative data, and in this case, we are talking about ratios here, right? And we need to look at the sample size. If the sample size is greater than 30, the magic number is 30. And if that happens, central limit theorem is applied. And this is huge because this implies that the sampling distribution is approximately normal. And then the next condition is the 10% rule. And we can safely assume there are more than 410 because we take the sample size 41 times 10. There are more than 410 bones in the population. So next part is the do part, right? So do part, assuming the null hypothesis is true, right? Assuming your whole is true, H naught, the sampling distribution will be a T distribution because the standard deviation of the population is unknown, right? Will be a T distribution. We're going to use a T distribution, also sometimes also known as student T, with a 40 degrees of freedom. Now, how do we get degrees of freedom? You take the sample size minus 1. So there are 41 data in the sample. There are 41 sample. We just take 41 minus 1, which is 40 degrees of freedom. And X bar, the sample mean is 9.27, and the standard deviation of the sample is 1.198. Now, I want to show you how I got that, right? So now I already put all the 41 into list 1, 41 data into list 1. So I go to stat, and then I go to calc, and I do a 1 var stats. So my first one, list is in list 1. I do not have a frequency list, and voila. So the X bar, you see that X bar is 9.27, right? Round to the nearest 2 decimal places. And the SX right here, SX is the sample deviation. It's 1.19, actually 199. I see. So 1.199. Anyway, so this is how we get the sample mean and the standard deviation. And I'll show you later on why we could have skipped this step. But we needed to find X bar. I want to show you how do we find X bar and standard deviation for the sample. So let's resume. Okay, so next thing is to calculate the T statistics, right? To calculate T statistics, you need your X bar minus mu divided by the sample standard deviation divided by root n. So the reason why, so T statistics has this formula, and which is why I wanted to show you how do we manually calculate this T statistics if that's, if you want to go about doing that. So which means you need to find X bar, the sample mean, which you also need to find the S of X bar, which is the standard deviation of the sample. So assuming all the data is correct, now you put it together. So the X bar is 9.27 and the mean is 8.9 divided by 1.198 divided by square root of 41. And then that comes up to 1.97. So this is a T statistics 1.97. So for the T distribution, it can be bell shape. We don't call it normal, so we call it a T distribution. And this is standard T distribution, which is the same as the normal distribution. We put a 0 as your mean in the middle, and then 1, 2, which is the standard deviation, right? The T star, actually, those are called the T value. So 1.97 is right there. You see that, right? And because the alternate hypothesis says that we are assuming, right, that's the null hypothesis is that mean is 8.9, and the alternate hypothesis is that the mean is not equals to 8.9. So it's actually a two-tailed test. So here 1.96 is the right tail. We need to put in the left tail, so negative 1.97 going the other way. So let me shade to the right and let me shade to the left of those two values. So now, why do I shade that? Because we need, those are the area for that actually will be your p-value. So p-value equals to, now I only need to do one time, right? One to find the area for the one tail, and then I just multiplied it by 2 because they are symmetrical. So to calculate the p-value for a T distribution, we use the TCDF, right? TCDF. and it has the lower, which we know now it's lower bound is 1.97, upper bound is 99999, and the next is degrees of freedom. You need to state the degrees of freedom. In this case, is 40. 41 minus 1 is 40, which is approximately 0.056. Now I'm going to show you where do I find the TCDF. So to find TCDF, you go to second vars, and then you see how number 6. So go to number 6. So he asks you for the lower, right? The lower in this case is 1.97. That's our T statistics. And we're only calculating for one tail. And upper will be 99999. And here the degrees of freedom is 40. Okay? So that's the value right here. And then we multiply that by 2 because it's a two-tailed test. So look at the value, 0.056, right? 0.056 round up to the nearest 3 decimal place. So that's how we calculate the p-value using the TCDF. Okay, so I want to show you how do I actually can go about using the calculator to help find the p-value. So using calculator to find your T statistics as well as to find your p-value. First you go to stat, and then you go to tests, and then you find the one sample t-test, also known as t-test, right? Also known as t-test. So, all right, let me show you. This is assuming that you have everything listed in your that you have already put in the list, right here. See, it's all the data. 41 data is my list 1. So I go to stat, then I go over to test. Now if you look down the list, the one that you need, the one sample t-test, is right here, number 2, t-test. So if you click on it, and it says it's blinking on data. Now if you are using data, which means you have a list, you just need to input this. Just choose it, right? And then your mean, right, which is your population mean, is 8.9. You just have to state that, right? Is it 8.9? Yes, it is 8.9. And then it said list 1. Yes, I put all my data in list 1. Frequency. So which one am I using? So you see how there are 3 options here. Now this 3 option is based on your alternate hypothesis, and in our alternate hypothesis we're saying that the mu is not equals to 8.9. So we need to click to the left and choose this one. Now when your alternate hypothesis is less than, let's say if you assume that your alternate hypothesis, your mean is less than 8.9, then you choose this one. If your alternate hypothesis, if you think that your mean mu is greater than 8.9, then you choose this one. So this is a two-tailed test, right? Not equals to. So pick that and draw. So voila. So see how the first line says mu is not equals to 8.9, which is our alternate hypothesis. Your T statistics here is 1.97, like what we calculated earlier. Look at the p-value here. P-value is 0.056, just like what we found. Okay, so let's go back. So yes, choose the data if you have a list, all right? If you have a list. If you do not have a list, then you will need to use the sample statistics, right? So let me show you again. Now if you choose, let's say if you choose stat, test, t-test. Now notice this. Notice that if you're not using data, if you do not have it in a list, and you press stat, you have to input everything yourself. So here we go, and the mean is, population mean is 8.9. See how the standard deviation here, the sample mean we calculated to be 9.27, okay, which we found, and the standard deviation is 1.056. 0.199, right? And yep, okay, the n sample size is 41, and we are choosing that, and we calculate. So assuming you do not have a list, and all this is your statistics, sample statistics that you already found, or it's given to you. So C, still the same answer. T equals to T statistics of 1.98. In this case, it should be 1.97, but rounding error, and your p-value is 0.055. So pretty close, okay? Because there's rounding error. Okay, so to conclude, right? To conclude, since a p-value of 0.056 is greater than the significance level of 0.05, just slightly bigger, and we failed to reject H naught, right? We failed to reject H naught. Now you got to be careful here. So if your p-value is exactly 0.05, we still, it's still greater, right? It's still equals to greater than, right? 0.05, we fail to reject. And in this case, if your p-value is so close to the significance level, I mean, that means there might be some error somewhere. I would advise you to actually do another sample, right? Get another 41 sample somewhere, and then conduct this t-test again. So we do not have significant or convincing or sufficient evidence to suggest that these bones have a length to width ratio different than 8.9. All right, so this is chapter 9.3 of tests about a population mean. Concept 2, the power of a test. So this is a new concept, right? A new vocabulary, power of the test. So to check for understanding, students will be able to interpret the power of a significance test and describe what factors affect the power of the test. Now, power is only related to the significance test. So when we do a significance test, then the power actually comes up from time to time. So let's dive in. A computer manufacturer requires each batch of processors it uses meets high quality standards. If the manufacturer finds convincing evidence that the processors use more than 70 watts of power in the normal usage, the batch will be rejected. A quality control engineer inspects a random sample of processes from each shipment and performs a significance test of the null hypothesis H naught is mean equals to 0.70 versus alternate hypothesis mean is greater than 0.70, where the mean, mu, is the true mean power usage in watts of the processes in a given batch. So question A, the power of the test to detect that mean is equals to 71 based on a random sample of 30 processors and a significance level of alpha equals to 0.05 is 0.75 to interpret this value. So to answer this question, you have to state if the true mean power usage of the batch of processors is indeed mean equals to 71 watts, right? If the true mean power usage, right? If the true mean is actually 71, then there is a 0.72 probability, right, that the quality control engineer will find convincing evidence for, right, you want to reject the null, right, for HA, the alternate hypothesis where the mean is greater than 70. All right? So I'd like to kind of explain a little bit about what the power of the test is. All right, so this is kind of a more it's an explanation, but I hope this helps clarify a few things. It's not going to clarify everything because this is a rather new idea. So it's the probability. It's the probability of rejecting the null hypothesis when it is false, right? The power of the test is the probability of rejecting the null. So let's say if the null is actually false, and you want your test to be able to detect that, right? To be able to reject the null when it is actually false. Power of the test is also you can look at it this way. It's a probability of avoiding a type 2 error, right? What's a type 2 error? Type 2 error is assuming your null hypothesis to be true when it is not so. All right, so it's the probability of avoiding a type 2 error. The third way to look at it is that it's a probability that a particular study will detect a deviation from the null hypothesis given that one exists. Okay, so power is equals to 1 minus beta. And what is beta? Beta is actually your type 2 error, right? Beta is type 2 error. Now, you don't need to know how to calculate beta. It's either going to be given to you or, you don't need to calculate beta. And you have to understand that beta and alpha is your significance level, right? And they're kind of related in a way, right? So as alpha decreases, as your significance level decreases, your beta actually increases. And then if you look at the formula above, if power equals to 1 minus beta, as beta increases, right, your power actually decreases, right? All right, part B, determine if each of the following changes would increase or decrease the power of the test. So explain your answers. So part 1, when you change the significance level, right, from 0.05 to 0.01, what's going to happen to the power? Now it's going to decrease. Why is the power is decreasing? Right? Because a smaller significance level makes it harder to reject the H naught when H naught is true, right? It makes it more difficult because, right, when we reject a test is when your p-value is less than your alpha, right? So if you reduce your alpha, your p-value has to be really small. So in this case, your p-value has to be smaller than 0.01 to reject it, right? So your power actually decreases, right? Because the smaller significance level makes it harder to reject H naught when your alternate hypothesis is actually true. So part 2, take a random sample of 50 processes instead of 30. Every time when you increase your sample size, what do you think is going to happen? You're going to get a more accurate statistics, right? You're going to get a more accurate statistics. Now, what does that statistics help to do to the power of the test? It's going to help increase the power of the test. Why? Because a larger sample size gives more information about the true mean value. So in this case, it's going to give you a better, more accurate, less bias of a true mean. I actually forgot about this. Part 3, right? The true mean is mu equals to 72 instead of mean equals to 71. So what's going to happen to the power of the test? Now it's going to increase, right? Why is it going to increase? Because it is easier to detect a bigger difference between the null hypothesis and not the null and alternate parameter value. Okay?